Okay, so yep, so we'll look at everything for mass spectroscopy, and in the same way as we did the others, and then we'll put all the spectra together, and this is what you're going to need to do for the task. Then we'll first look to get you achieved, and then we'll look at going for merit and excellence. So that's sort of what a mass spec does. You get different parts. First, you turn your sample into a gas. So it has to be put into a gas, so it gets heated to get to a gas form. Then it gets passed through this electron beam and it ionizes it. So an electron, this electron beam will knock out an electron from the molecule. If it only knocks out one electron, if that bit goes through, that'll show the mass of the total molecule. But it can also break bonds, and so this is called mass spectrometry and not actually mass spectroscopy, because it doesn't look at the interaction of light with the molecule. It actually just smashes it up with the electron beam. So you can't get your sample back again because it's in bits and pieces. So we basically, once we've ionized it, we put the electron beam through it and it gets broken up. And so it gets broken up into cations and radicals. Now don't worry about the radicals, just ignore them. It just means it's got an unbonded electron, that's all. The cation is important because the cation, being a charge, is affected by a magnetic field which is over here. So when my cations and radicals come out of this electron beam, they get accelerated, and you don't have to know why, but why this bit is important, this part of the mass spec, is if you accelerate, you know when a train is moving and a car is moving, which one can stop more quickly, the train or the car? The car, because it's got a less mass, a lower mass, and the train, because it's got enormous momentum, is going to carry on going straight and it'll take longer to stop. So it's the same thing here. You accelerate your cations and radicals and they come through here, and as I say, ignore the radicals. They come through. The heavy ones just want to keep on going straight. I mean, they will bend in the magnetic field, but they'll only bend slightly. So the ones over here are the ones that are the ones that are the heaviest, whereas the ones that bend quickly are the lightest. So that's how we can get this range over here. So that's the ions accelerated, and then they go through the magnetic field, and this is where it does the bending, so it doesn't go straight through. The bending depends on the charge. So the more charged, the more it interacts with the magnetic field, so the more it's going to bend. Now in reality, that electron beam pretty much knocks out one electron, and then it's harder to knock out more electrons, because now you're trying to remove electrons from something that's already positive, and you know it's quite hard to remove a negative from something that's already positive and make it more positive. So most of the time it's only a +1 charge, a cation, a singular cation. It's not a 2+. So this range over here depends really on the mass rather than on the charge. But we do sometimes get a 2+, and that's why we might get a funny peak somewhere which we can't explain, and that could be because it's a +2 charge. So how much it bends depends on the mass, because the bigger the mass, the more it wants to go in a straight line, and the charge, because the more charged, the more it's going to bend. So it's that sort of breakdown. But as I say, pretty much all of them is a single charge. Now, when it comes here, obviously if you've got a fragment with the same mass-charge ratio, it's going to keep on pinging at the same place, and the more it pings at the same place, the bigger that peak is going to be. So this is as a detection screen which measures this mass-charge ratio, but the charge is normally 1. So what can we learn from this? The more stable the fragment, the taller the peak. So if not much has been broken off and it doesn't break down further, it's going to reach the detection screen a lot, and so there'll be a big peak. You can, though, get a big peak made up of a number of fragments, and you will see this later. So as long as they've got the same mass to charge ratio, they're going to ping at the same place, and so but it could be from different fragments all landing up in the same place, as long as they've got the same mass to charge ratio. And then because we're working with isotopes, we're working down to the atomic level now, we can't take average masses anymore. So we're not looking at the mass of carbon is 35.5. What we're looking at is we're looking at the isotope of chlorine. Sorry, when I said the average mass of chlorine is 35.5, we don't use that figure in here because we're down to the atoms now. So chlorine, we're using the chlorine isotope of 35 or 37. We don't have any averages. And because we don't have those averages, we're going to get a peak depending on which isotope comes through. And I'll show that later. So carbon 12, most of it's carbon 12, so that will be a much bigger peak than the 13 peak. There's only going to be a tiny one. You'll see like it's around about 1/60th, 1/50th or 1/60th the size. And we'll have a look at examples. Chlorine, 3/4 of it is 35, only 1/4 is the 37 isotope. So you're going to have the 35 chlorine isotope being 3 times the size, because 75 is 3 times the size of 25. So it'll be 3 times the size of the other one. And if it's 35 and 37, what is the difference between 35 and 37? The difference in number? 2. So assuming that the charge is all going to be the same, and as I say, it pretty much is, you'll see that isotopic peak 2 units higher because there's a difference of 2 between 35 and 37. And then bromine also has got an isotope, and they're nearly in a 50-50 ratio. Bromine 79 is 51%, bromine 81 is 49%. So you'll see peaks that are pretty much the same height, the lower peak being slightly bigger in size. But again, the difference between 79 and 81 is 2. So you're going to see that same difference between the peaks of 2 units apart. So let's have a look now. This is a spectrum. So what do we look at? First of all, what we need to identify is this mass charge ratio. But as far as you're concerned, take it as charge is always 1. So the peak numbers corresponds to the atomic or the molecular mass, or the mass of that cation fragment. Okay, so that's the first point to remember. Then the next thing you look at is right as far as you can to the right for the heaviest peak, the biggest number. Now you'll notice there are 3 little peaks here. There's one at 71, there's one at 72, and there's a tiny little peak at 73. Now I've told you the molecular iron peak is 72 because what do you think that little peak 1 up from the 72 is? What do you think that peak that's round about 1/60th or so of, what do you think that would be due to? The carbon 13. So this is what I mean by the isotopic peak. That is due to the number of molecules in the sample that actually have carbon 13 somewhere in them, and that'll give them a peak up there. This little peak next to it, the one down, always means a loss of hydrogen. So somewhere along the line it's lost a hydrogen, and we'll look at examples of what's more likely to lose hydrogen compared to others. And so we look at the molecular iron peak, and we can get lots of information from that, which we'll look at later. And the other peak you need to look at and explain for excellence is the other tallest peak. Now the way they do a mass spec is the tallest peak is always made 100%. Because we're comparing these ratios. So we're just saying that the most stable peak is this one, make it 100%, and these are therefore relatively less stable, or these smaller peaks. So you can't compare two mass spectra and say the fragment in this peak is more stable than the fragment in that peak by looking at peak size, because this is relative height within the sample rather than an absolute height. Does that make sense? Okay, yep, because they're all altered so that the biggest peak is 100% regardless of how much it is. Okay, and then the others are proportional to it. Right, and then you can see if you've got a tall peak, there normally is a little peak to the side, one up, and that's the isotopic peak again. Okay, you'll see these one and these at isotopic peak there too. Most of them are isotopic peak. That's not an isotopic peak. Part of it would be, of course, because there's a little bit of the isotopic peak of that one. So this one is a fragment. It could be a loss of hydrogen from this one, or it could be a loss of something else from other ones up. You are not expected to explain every single peak. In fact, for excellence, I expect you to only explain one peak. And it's normally the base peak, but sometimes you have to use another peak just to say why you've chosen this isomer and not another isomer. Okay, so that's more or less what a spectrum looks like, and as they have pointed out, the loss of hydrogen if it's one down. And the other fragments are, as I say, less stable. Now, what can you find out from a mass spec? A mass spec can give you a lot. First of all, it gives you the molecular mass. And you need the molecular mass when you want to work out the formula. In other words, how many carbons, how many hydrogens, how many oxygens, nitrogens, and so on in the molecule. So that's really important. And for achieved, if you get that one right, you can tick your box that you've done something from the molecular ion. Although I always say, just in case you, so from the mass spectrometry spectra, but I always say do at least two things, because you may have got one thing wrong. So I want you to do at least the molecular mass and one of these things at the absolute minimum, because it also tells you particular ions which can be present or absent. And the one that always tells you to be present is nitrogen. If the M+ peak is odd, it means it's containing one nitrogen or odd number of nitrogen atoms. And I promise you, I won't give you a molecule that has 2 nitrogen atoms in it, because if you have 2 nitrogen atoms in it, then the molecular ion peak is even, and I don't want you to be confused. So you will only get, if you get nitrogen given, it'll always be a single nitrogen. And what you'll find is the molecular ion peak is odd, and you will get fragments that are even. So, and we'll look at examples. Chlorine, remember we got those 2 isotopes of chlorine? So in your molecular ion peak, you should get 2 peaks in a 3-to-1 ratio, the lower one being 3 times higher than the upper one, and they should be 2 units apart. That's the way when you don't confuse a loss of hydrogen. Say there's been a loss of hydrogen and that one is quite a big peak, more stable than the actual molecular ion, because that's only 1 unit apart. So for chlorine and bromine, they're 2 units apart. The other thing with bromine is, of course, if you get a molecular ion of 75, would that contain bromine? If the mass of bromine is 79 and 81. Yep, quite correct. If the mass is pretty much under 95, it's not going to have bromine, because remember the bromine is 79, plus it's got to have a carbon on it, because you're not going to get just bromine by itself, plus a hydrogen or 2. So pretty much 95, 100, it's got to be over that for it to have bromine. If it's under that, even though it might look like anything else, you know, the 2 units apart, 1-to-1 ratio, it will not be bromine. Then this bit number 3, we'll look at a little bit later in the lesson, and we can actually work out the isomer based on the fragmentation pattern. So this is what's needed for excellence, and you need to have some discussion on this for merit as well. You do not need to use this for achieved. And basically what we're saying here is a tertiary carbocation. So if you think of a tertiary alcohol, a tertiary haloalkane, think of it exactly the same way, but instead of having an OH on it, that carbon's got a positive on it. So tertiary carbocation is more stable than a secondary, more stable than a primary, And then we're going to talk about acylium ions being stable as well as the nitrogen version of it. And then with the 1 unit less, that loss of hydrogen, it tends to be from alcohols, amines, aldehydes, and carboxylic acids. Tend to have a loss of 1 hydrogen. And then other things, loss of 15 means you've lost a methyl radical, loss of 29, you've lost an ethyl radical. But as I said, don't try and explain every fragment, or if you've got a fragment there that you can't explain, don't worry, because you can get rearrangements, and that's way beyond this course. Okay, and as I said, don't confuse the molecular ion peak with the isotopic peak. Remember, isotopic peak for carbon 13, bromine 81, and chlorine 37, because they're in the minor amounts, they're considered to be isotopic, not the main peak. Any questions so far? Okay, good. So now we're just going to have an overview. We'll look at 4 samples of the different elements. So if, we've got here, I've told you what the molecule is. Okay, it's a nitrogen containing one. This is what it looks like. But the reason why we know it contains nitrogen is if you look at here, that's 80, that's 85, 86, 87. So the molecular ion peak is 87. It's odd. So it contains nitrogen. You can confirm it contains nitrogen because the molecular ion peak is odd. This little peak slightly 1 up, that's the isotopic peak. And what do you think this little peak down here is? The tiny little peak over there, barely visible. That's the loss of hydrogen. And as I said, amines, alcohols, aldehydes, and carboxylic acids often have a little peak there. And sometimes that peak can be bigger than the one and than the molecular ion peak. And that's just because nitrogen oxygen can stabilize a cation. Okay, so that's the way we look at a spectrum that's got an odd peak. We know it contains nitrogen. And if you see an even peak, like this one at 70, it means this peak is going to contain nitrogen. So even peaks will contain nitrogen. Most amines, particularly primary ones, will have a peak at 30. And that's a NCH2, NH2CH2 sort of stabilization with a double bond between them. That gives you the peak at 30. So that's nitrogen, and we'll look at that one later when we look at fragments. Now, if you add up all the carbons, you'll see there's 2, 3, 4, 5 carbons, so 5 times, remember we're going on isotopes, and we're going on the major isotopes, so 5 times 12, notice I haven't said 12.0, I've just said 12 because it's carbon 12 we're using. We've got 13 hydrogens. They've only got a mass of 1 because we're only looking at protium, we're not looking at any averages. And nitrogen, around about 99.9% of nitrogen is in 14. So we've got 1 with 14, and that adds up to 87. So your structure that you draw up when you get to that point should equal 87, or the molecular ion peak. Here's one containing chlorine. Now, it's not that clear, but if you look down here, okay, can you see there are 2 peaks 2 units apart? And they're too small to have isotopic carbon peaks, so you won't see any of those. But they're 2 units apart, and can you see there's actually 2 units apart here as well, in this area. There's a tiny little isotopic carbon peak over there for this one, but you don't see anything from that one because it's just too small. So if you see in a 3:1 ratio, you know it contains chlorine. So that is the important thing. So notice I've made the molecular ion the lower one, okay, the one where it includes chlorine 35, not chlorine 37, because chlorine 37 is not as common, so it's the isotopic peak. and that's the isotopic peak there. And you'll recognize it always 3:1 ratio, 2 units higher. And you know this fragment also contains chlorine because it also has that 3:1 ratio, 2 units apart. This one is not 3:1 ratio. It is 2 units apart, but if we go 1, 2, 3, is it in a 3:1 ratio? No. So you know that does not contain, whoops, I can't see it there. These do not contain the chlorine. Or if it does, this one also has another fragment. Because remember I said anything with the same M to Z ratio, it gets put in that place, that ping. So this may consist of the fragment corresponding to that one plus other things as well that doesn't contain chlorine. Okay, this is not 2 units apart, so these do not contain chlorine. Okay, if you go 106 subtract 35, you must probably land up with this one at 106 subtract 35. Actually, it would come to about 71. So this is also lost a hydrogen as well over here. Okay, and if you add them all up, you should, so once you've got your formula worked out, it should add up to your molecular ion peak. Here's one containing bromine. Can you see that very clear, nearly identical peaks? Okay, there it's a bit clearer where the one to the left is slightly higher. You're going, Okay, so it's 2 units apart. Notice the numbers. Okay, it's above 100. So the molecular ion peak is 136 and the isotopic peak is 2 units higher. And you'll know this fragment also contains bromine, so something else has been knocked off. And as I say, notice the molecular mass. It's always, definitely above 95, usually above 100. Okay, and then there I've just added it all up so you can see. Do you notice I don't use the periodic table value of 80? I use the isotopic value of 79. So we're working in isotopes, not averages. I'm just stressing that all the time. And here's one containing oxygens, and where I'm showing the loss of the hydrogen. Sometimes you do get peaks higher up, but I will tell you that those are impurities, because sometimes there's a bit of solvent that gets through or something, and you might get some little pings higher up. But you will be told that they're impurities, so you must ignore them. So you know that this area is the important bit, and you've got to decide which one of these three is the isotopic one, so is the molecular ion. And I hope you can see that this one at 74 is the molecular ion, because this one over here will be the isotopic carbon-13 peak. And there's, you can't have a 3:1 ratio of chlorine between the one, these two, because the one in the middle is too tall. It's got to be empty between them if you want it to be the chlorine. So you've really got the three peaks 1 unit apart. Yes, and so you've worked it out there. So that's the loss of the hydrogen, and that's because the OH can lose that hydrogen quite readily because the oxygen stabilizes the cation. Okay, and that adds up to 74. Great, well done. So let's practice. Have a look at that molecular ion peak, and can you work out what is there, what is not there, based on what it is. So which elements are present? Nitrogen. And it's nitrogen because it's an odd number. Okay, so we know it's a nitrogen, and there's an M+1 peak, and that's the loss of hydrogen. And we can say it's not chlorine and it's not bromine because we don't have those particular ratios. Now I can see you typing, yep. And we're obviously going to have carbon. We're always going to have carbon and hydrogen, so we don't really have to state that. Although when we do the IR mass spec, IR and carbon and the carbon-13, we can obviously say there's carbon present based on that. So it's this particular compound, and we lose that hydrogen over there, and that's why that's quite a stable peak. It's quite a big peak there, because it's stabilized, the nitrogen's been stabilized by both sides. Secondary amines tend to lose hydrogen quite easily. Right, and then we add it up, and there it gets to 87. So it's just a variation of the other one we had. And we can clearly state it contains nitrogen, and we can clearly state it doesn't contain chlorine and it doesn't contain bromine. Now, you must say why it doesn't contain chlorine and why it doesn't contain bromine. Don't just make a statement, no chlorine or bromine. You must say why. Okay, so you've got to say it doesn't have the 3:1 ratio 2 units apart for chlorine, or the 1:1 ratio 2 units apart for bromine. Here is another practice. What is this? What elements do you know are present and which ones are absent? So first present, Br. And you can see that straight away because we've got 2 peaks, 2 units apart that are more or less the equal space. Okay, now, and it's the high mass, correct? Now, it doesn't mean to say if it's a high mass, it can't be something else, but you do need a high mass if you've got bromine. Now, what is the molecular ion peak? 122 or 124? 122, great. Okay, so there it is. Now you should then, so that's just explaining how you get that 122. You should be able to say why there's no nitrogen and why there's no chlorine. Okay, you can't say why there's no oxygen because you actually can't from a mass spec. You could suggest supporting evidence that oxygen could be present if you're losing hydrogen, but it's not, you can't be definite. So mass spec, you can't be definite about oxygen. And you're quite right, you've lost 79 to get from there to there. So, this peak. So that gives you that fragment over there. We'll do fragmentation later. What element is present here? Or you could say what's not present. Because sometimes you can't say what's present, but you can say what's not present. Like you could say there's no nitrogen, no chlorine, no bromine. Yep. So, and there's also, if you've got there, that's 85 over here, so this is 86. So it's even, so there's no nitrogen either. So we know it contains carbon and hydrogen, and it may or may not contain oxygen. It probably contains oxygen because we've got this hydrogen, one loss of hydrogen here. So probably oxygen, but we can't be definite. Okay, so there's all the bits. And that's actually what it is. It's an aldehyde, and that's how we get to the 86. So we may have oxygen, but we can be very definite and say it doesn't have those. Okay. Now, in terms of this one, number 4, what element is present? Cl. And we can see that very clearly, 2 units apart, 2 peaks, 3:1 ratio. Now, which one is the molecular ion? The 78 one, correct. And the other one is the isotopic peak. Good. And that's how we add it up. Now, as I say, I wouldn't expect you right now to know that it's this one and not say chloropropane. We will do that later though. And so we know it's definitely not nitrogen because it's not an odd number, and we know it's definitely not bromine because although these are 2 units apart, it's not, sorry, I've gone blank, it's not 1:1 ratio. And of course, the third reason is, yep, so it's not 1:1, correct. And look at the mass, bromine is 79 and 81, so we don't have a peak at 81. And you're going to have a molecule and not an atom, so the mass is too small for bromine. Okay, and what about this one? What do we have here? Now you may have to look at it and say what's not there rather than what is there. Here we've got something at 85, but we've also got one at 86. Is that 2 units apart? No. And if it's going to be even like that, it's got to be bromine for it to be similar in height, and we know the mass isn't tall enough. No, it's not impurities. I would tell you if there were impurities. So this is a case where the molecular ion is, okay, that was why it doesn't contain bromine. It's not heavy enough, it's not 2 units apart, and the third reason is, remember, the lower peak needs to be slightly higher than the upper peak. So in here it's the other way around. The upper peak is actually slightly higher than the lower peak. So we know it doesn't contain bromine. The M plus ion is actually this higher peak because, as I said, it doesn't fit the bromine. I would tell you if there was an impurity. So if the one was at 85, we can't explain the one at 86. So if you look very carefully, yep, the loss of hydrogen. So if you look very carefully, there's a tiny little isotopic peak from the carbon-13 at 87. And this is actually the loss of hydrogen. So basically we're saying that the molecular ion peak is pretty much as stable as the fragment that has lost a hydrogen. They're more or less equally stable. And so probably has an OH or an aldehyde or carboxylic acid. You know, it all sort of helps support that sort of argument. And there's that loss of hydrogen, and this molecule actually contains an OH. So that's what's happened there. Okay, and there to show, you know, you always got to add up your structure to see does it match your molecular ion peak. If it doesn't match, you've made a mistake. And so we probably have got oxygen. We can't be absolutely definite, but we're definite that there's no nitrogen because it's an even number peak. We know it's not chlorine because there's no 2 peaks, 3-to-1 ratio, 2 units apart. No bromine because there's no 2 peaks, 1-to-1 ratio, 2 units apart. Okay, so that's what you need to do for the achieve level. You need for merit and excellence to do something about the fragmentation pattern. I mean, for achieved, you could have something, so if you stuffed up into something else, but you got a fragment, right, that still ticks the box that you could interpret something from a mass spec. So remember what I said, the more stable the fragment, the taller the peak. So a tertiary carbocation is more stable than a secondary, which is more stable than a primary. And then an acylium ion, so something that contains a carbonyl carbon, and if that carbon is a cation, or one containing nitrogen, also tend to be stabilized, because the lone pair on the nitrogen stabilizes the one on carbon, and the lone pair on the oxygen stabilizes the positive charge on the carbon. So here's an example. Now, is this a primary or a secondary or a tertiary carbocation? So in other words, the carbon that's got the positive charge, it's primary, correct, because it's only attached to one other carbon. And so we only get stabilization from the electron density on this side from one side. Compare a secondary, that's a little bit more stable because we've got carbon or electron density from 2 sides that can sort of feed into that cation. And then tertiary, sorry, we've got from 3 sides, and that's why a tertiary is more stable than a secondary or primary. Then if we look at the acylium ion, now you don't have to know resonance at all. So first of all, we've got some what we call inductive effect. All these green arrows are showing inductive effect. That's the electron density pushing in. This is what we call resonance, where the lone pairs on the oxygen feed in the electrons and the positive charge gets shared out between the carbon and oxygen. You don't have to know that at this level. I'm just putting that in to try and explain why the acylium ion is more stable. That's the only reason why I'm putting it in. The same thing with the nitrogen. It's to explain why a carbon next to a nitrogen is more stable than one not, because of that sharing, that resonance effect. Okay, so as long as you remember that pattern, you can use it to work out fragments, and we'll do lots of examples later on. But let's just work out which one of these, of A or B, is going to be more stable. So ask yourself, is it a primary, is it a secondary, is it a tertiary? So which one B, correct. Okay, and for 2, which one of A and B? A, correct. Which one for number 3? A, correct. And that's for number 2A, it's because this is tertiary compared to secondary over here. This is secondary, oh, sorry, I've clicked. And that's only a primary, that's still considered still primary. And then here, this is a psyllium ion compared to a primary. Now, a psyllium ion could be as stable as a secondary or tertiary carbocation. Sometimes, you know, you can't really make a judgment, but it is definitely more stable than a primary, because it just simply depends what else is on the psyllium ion, you know, what's around it. Okay, now you will be given a table like this in the task, just to help you so you don't have to always keep on adding up the fragments. Remember though, there could be other fragments there. We don't give you all the fragments, but use this table as a guide to look for the presence of these peaks. So something at 43 could be a propyl group or isopropyl group, or sorry, a 1-methyl-ethyl group. Something at 45 could be from a carboxylic acid. Otherwise, look for the loss of these numbers. So if you've got a molecular ion at 106, you can look at something for 15 down, and if there's a peak 15 down, you've lost a methyl group. So there's 2 ways to use these fragments, either a loss or it's showing an actual peak. It depends on whether it's lost the radical or if it's formed the carbocation. Now here's an example for working out isomers. So using fragmentation patterns. So say we've worked out the formula. We know what the molecular formula is, but we're not sure, you know, how the carbons go. Now, there obviously are more isomers you could draw for this. I've said we've got the ketone based on the other 2 spectra, and I know we can draw 2 isomers, but I didn't have space to show all of them. But can you see this pattern belongs to there, and this compound has this pattern? Are they the same or are they different? They're different. So this is how we can use the mass spec to match the isomer. So let's have a look. Both of them 86 because they're isomers. Okay, so there's no difference there. The base peaks are different though. So let's look at the base peak for this one. We've got to try and find a fragment in this molecule that will add up to 57. Now remember, an acylium ion is stable, so we could break it either on this side of the acylium ion or on that side. So if we break it over here, we get this fragment. Okay, so there's the fragment, and if you add it up, it goes to 57. And what we can also look at, can you see this ethyl bit there? If we had something at 86 and it's going to 57, subtract 57 from 86, 29, and that adds up to this fragment over here. So we know we've lost an ethyl fragment to get this. Compare it to the base peak at 43. Now it doesn't mean to say that this isomer forms as much at 43 as this one does. Remember I said you can't compare between spectra. You can only compare within a spectrum. So where does this 43 come from? Well, if I break it over here, I can get this carbocation. I can get this carbocation that's secondary, that adds up to 43. But if you look carefully, I can also have that carbocation. So here's a case where I get 2 different fragments that add up to the same peak. So that's why this peak at 43 is so much stronger. Look at that tiny peak at 43 there. There's nothing here that's going to give me 43, but there are 2 things there that give me 43, and both of them are stable. One's a secondary and one's a acylium ion. So that will clearly help you work out, you know, what the structure will be. I can also use other peaks. So there I'm showing that, I mean, there could be a loss of either fragment to make the 43. I can use other peaks as well. Here's a peak at 29. So where would that peak come from? So if I cut it over here again, the same place, that adds up to 29. I know it's primary and it is quite a big peak. It could also, as I say, the peaks could come from somewhere else, so it could also be from another rearrangement that's made it bigger. But you can see it's certainly not as stable as a psyllium ion because it's not as tall as that peak. And if I looked at this one, can you see it's got a peak at 71, which this one does not have? Well, it does, but it's tiny, tiny, tiny. So this peak at 71 we can explain if we chop off a methyl, because that's a difference of a methyl. And if we do that, we get a stabilized psyllium peak, a psyllium ion, and there it is, adds up to 71, and I've just lost a methyl. So can you see how you can argue which, if you were given, for instance, this mass spec, and you had to decide which one of these two molecules it was, if you can have some sort of supporting evidence to the one you've chosen, we don't expect perfect answers, so don't be intimidated, but we do expect you at excellence level to be able to support your chosen isomer. You can't just say, oh, I think it's this. You've got to use fragments to show why you think it's that. So you've got to explain the base peak certainly, and perhaps one other peak for excellence. Okay, and notice there's no real peak at 29 because I don't have really an ethyl. Because remember, that's not an ethyl, that's a propyl group. I've got 3 carbons in there. So I don't really have a peak at 29 because I don't have an ethyl in there. That's another reason why this spectra can't match that one, because I don't have ethyl. Right. You are typing there, so I'll just carry on. I can go back if you need me to. So here's, okay, yep, and a carbon, yeah, well, a carbon chain can fragment, but if I removed another methyl, I'm going to have a carbon with 2 positive charges on it, and that won't make it 29 anyway. It'll make it an even number. And anyway, then it's the mass charge ratio changes anyway, so it'll shift down. Yeah, so you can get the carbon chain to break quite easy, but it's got to break in the same way. And then that one, if I just go back, I can't chop off this methyl to get an ethyl, because I won't. I don't have CH3CH2 with the methyl gone. I can't get a CH3CH2 fragment here anyway, because by chopping something off, because it won't let me do it. You can sometimes get small peaks from rearrangements. They will happen. But I'll always choose simple ones where you can actually work out the peak. Right, so here's one. So we know it's a secondary amine from the IR because it's got that single triangular peak in that area above 3000. And now we're trying to work out what isotope it is. You could draw more isotopes than these, but as I say, I could only fit 2 into the slide. So let's see which one's which. Well, they're both 87, odd number because they contain nitrogen. Let's explain this base peak. So we can chop it either this side or that side of the nitrogen, but we've got to get 58. So can you see this bit here adds up to 58? And that loss of 29 is a loss of an ethyl, just like we had before. My base peak at 72, can you see it's only tiny over here, but it's enormous there. That's where I've just simply lost a methyl. Now here, you could also get that peak at 72 if, say, this methyl breaks off or that methyl breaks off, but then you've only got a primary carbocation. Here you've got the nitrogen stabilized carbocation when that methyl breaks, and that's why it's so stable and therefore it's so tall. So you've got to explain why, what would stabilize it that would give it such a tall peak. And that's because it's nitrogen stabilized. You don't have to necessarily have drawn that double bond on there. This drawing program wouldn't allow me to put a charge on the nitrogen without putting a double bond in. But you could have just drawn a single bond and put the charge on the carbon. That would have been perfectly acceptable. Right. And what else can we do? I said the loss of the methyl from that being chopped off. We can explain that 44 peak by chopping at the other side. Now remember, if we've got a nitrogen-containing compound and we've got peaks that are even, they tend to contain nitrogen. So this is the other bit, okay, the nitrogen with the ethyl. And this peak at 44 is the same thing as well. Can you see in both of them, we've got the nitrogen with an ethyl, giving us a peak at 44. Here's at 44, there it's at 44. Now, as I said, we can't say this is more stable than that. We can't say that, because remember, we can't compare. We can't say this peak is taller than that peak, and therefore this must be more stable. You can see they're identical. It's just because within this fragment, this is particularly stable, and this one over here is particularly stable, so that one is very small by comparison. Okay, that's just to explain. You'll always tend to get something at 30 with nitrogen, by the way. Okay, I meant to ask any questions. Does that make sense? Okay, right. So here's another one, and both at 72. And really, we've got to try and work out, could it be straight chain? Could it be a branch chain? Would we get a secondary carbocation? That's really what we're looking at. So we've got something at 43 here. We've also got something at 43 on this side. But if you look over here, I have a primary carbocation being formed in this one with a loss of an ethyl. In this one, I've also got at 43, I've got a secondary carbocation being formed, okay, with a loss of an ethyl. Here, though, so there's no difference between them as such. They're both tall peaks. So we've got to look at to see what's different. And what's different here is this peak at 57. It's very tall in this one. It's not very tall in that one. So we've got to try and explain that, because these look similar to that. This sort of looks similar to that. So we can only look at the one at 57 to try and work it out. So to get that peak at 57, I must have lost a methyl group, and I get a primary carbocation with the loss of a methyl. In this one, I get a secondary methyl. And can you see a secondary methyl, sorry, a secondary carbocation, a secondary carbocation? Can you see they're both similarly stable? And that's why the peaks are similar heights, because they're both similar. Here, there's, I agree, there's a primary carbocation. I mean, they're both primary. But we can compare this one, or I mean, this could come from a number of fragments breaking it up, because it could break up from this side or it could break up from that side. So this peak is made up from the two different bits. I mean, you could argue from any way, but your main thing is that you've got a secondary carbocation which could explain this. And that's why you're most probably going to have that structure rather than that. And that's the loss of a methyl. And then we've got peaks at 29, and that's because that's an ethyl group, and we have an ethyl group in a number of places. So there's an ethyl group over there as well that could explain the 29. And as I said, it looks as though this is more stable than that, but it's not. Oh, one other thing that's different, and that's the main difference. I left this one till last. Can you see this one's got lost at hydrogen compared to there? That's only a tiny peak in comparison. This is the hydrogen that'll get lost. And if I lose this hydrogen, what carbocation is formed here? A primary, a secondary, or a tertiary? Actually, a tertiary, because can you see this carbon is attached to 3 other carbon atoms? And that's why I've got quite a tall peak there, because it's unusual to get a loss of hydrogen in just a straightforward alkane. You tend to see a loss of hydrogen when you've got oxygen present. So this is quite unusual, but because you're forming a tertiary carbocation, that's why you have that. You don't form a tertiary carbocation here. You can only form a secondary at most. so you don't really get much of a peak. And then what I was just trying to show here is that if I brought this down to sort of compare, can you see it's similar heights if I was trying to do the distribution. So this peak is as stable as that peak. But by this I brought it down so that the sum of the heights of all these peaks adds up to the sum of the heights of all those peaks. You don't have to do that, of course. Okay, so putting it all together. Actually, I didn't make a note of when we started, so let me know when you've had enough. Okay, so what do we do to put it all together? You start off always by looking with the molecular ion, a peak on the MS, because that tells you the elements present, and it tells you the total mass of this substance. Then you look, as I say, for the elements present or absent. You know, you can guarantee the presence or absence of nitrogen, chlorine, and bromine. And then you look at the functional groups on the IR, and you look for confirmation in the MS for the elements. So if you think a nitrogen is present, do I see a C or NH stretch in the right area of the IR? You know, this is sort of thing you've got to, if I think a Cl is present, do I see lots of peaks in the fingerprint region? So just look for the confirmation, and then look for the NMR. For excellence, you must tie the mass spec together with the IR and the NMR. So your evidence must come from all three places when you confirm something. Then you want, when you want to look at the formula, you get the mass from of the molecular ion from the mass spec, and then you get the number of carbon environments from the NMR. How many peaks? Because that'll tell you the minimum number of carbon atoms. If I've got 3 peaks, I've got at least 3 carbon atoms in that molecule. Then you work out your possible formula on the elements present, and then you work out if my IR is showing a double bond, like a C double bond O or C double bond C, the formula I come up with must show that unsaturation. So remember this CnH2n plus 2 for a saturated alkane or haloalkane or so on. Remember, oxygen has no effect on the ratio, and chlorine and bromine are part of the H ratio. Okay, so if you've got any chlorine and bromine present, then you count it as one of the hydrogens. Nitrogen, remember, always has got 2n plus 3. It's always got an extra hydrogen present because nitrogen can bond to 3 hydrogen atoms. If it's got 1 double bond, so 1 unsaturation, remember the ratio CnH2n plus H2n, or if it's a nitrogen, CnH2n plus 1. And then if it's 2 unsaturations, it'll be CnH2n minus 2 or CnH2n minus 1, sorry, because I've always just got to subtract 2. So let's have a go for it. This slide is just to show you will be given this information. So you don't have to learn things off by heart. It's given there. Just you tear it out of your task, and then you have it there ready and write on your spectra, you know, compare and confirm all these bits and write it on your spectra. So here's the first one. We'll do 5 practices and then we'll carry on. You'll be given something like this, 3 spectra, and then you've got to work out what the substance is, what the molecule is. So let's first get it down to the formula. So, okay, yep. It actually is not that difficult, particularly to achieve. It's actually dead easy to achieve. Because remember what I said, the first thing you look at is the mass spec, and you look for the molecular ion. You're right, it's an alcohol. So, but you're going to be systematic, because that way you're not going to miss anything. So this molecular ion is 74. Okay, I know it's very small, so you most probably can't see it very easily. And once you've got that, you can work out by looking at the molecular ion, do I have nitrogen present, chlorine present or a bromine present? No. And explain why. Talk about the odd number or the ratio, you know, the fact that it's an even number and so on. And then also correlate it. Yep, and I'll get onto that one now. Correlate it with the others. So say there's no chlorine, no nitrogen present, and we don't see a peak in the IR, or if there is, it's covered. We don't really see a peak. Remember, the peak is around about here for a CN. We don't have that. Okay, we don't have chlorine peaks over here. So, you know, don't just base it on there for excellence. Look at the mass spec and the IR. Right. So once we worked out the elements present and absent, okay, of the chlorine, bromine, and nitrogen, now we look at other elements, and you've already said it's an OH, so we know an oxygen is present. Okay, we've discussed that, but I mean, you've got to write down, even if it's on the spectrum or on your discussion, why there's none of those. And that's just to look at other spectra to confirm. So don't just take it from one place, look at all three. Now we know an oxygen is present because of this OH. Okay, and we know an oxygen is present because that carbon peak has been shifted down and it's in the right area for a CO bond. Alright, and there are 3 carbon environments, so we know there are at least 3 carbons. So now, as I say, follow a systematic pattern. So look for the 3000, we've got an alkyl, and that corresponds with those. Those look like alkyl peaks. And we'll fine-tune them further down the track when we go on to isomers. Then we look, we don't have any alkenes, sorry, I should have said that. And then we look further to the left, and we've got an OH. And we've got a peak here, just because remember for an ester, it's round about 1000, so we've got like a CO peak, and that could be the CO peak. But we don't have an ester. Why not? If we had an ester, where would it be? Round about 170, correct. So although we've got the CO peak, that CO is from the carbon attached to this OH, and that's showing over there. We know it's not an ester because we don't have a carbonyl and we don't have the corresponding carbonyl over here. Okay, so we also, as you pointed out, we had a loss of a hydrogen, and that's quite common with OH, aldehydes, carboxylic acids, or nitrogen amines. But that supports that we've got an alcohol. Right, and we know there's no alkenes and no carbonyl groups. And we can say there's no alkenes, no carbonyls. Please say what's not there, even if it's on the spectra. You know, just write it on there, you know, in that range. You can draw an arrow from one side to the other. Remember, alkenes are from about 100 to 150, that area. So show that you've understood that. So to work out the formula, I've got 74 as my molecular ion. Do you see I'm telling you where I'm getting my information from? If in your discussion, say where you're getting your information from. If you're writing on your spectra, it's obvious where you're getting it from, but in your discussion, you need to state where it's from. So we know there's 3 peaks, so 3 carbon environments. We know there's 1 oxygen present because of this OH over here. And so if we add up what it could be, if our mass is 74, we subtract the 16 for the oxygen. All the carbons and hydrogens must make up 58 of the mass. Can you see that? 74 subtract 16. So if we've got 3 carbons minimum, 3 times 12, because the atomic mass of carbon is 12, is 36. Now, can we have 3 carbon atoms surrounded by something like 36, 46, 56, 20, 22 hydrogen atoms? Can we have 22 hydrogen atoms surrounding 3 carbon atoms? No. So, you know, it's got to be in the right ratio. So we know we've got to have more carbon atoms. So if we try 4 carbon atoms, 4 times 12 is 48. Now, can we have 4 carbon atoms? Sorry, can we have 4 carbon atoms surrounded by 10 hydrogen? Yes, we could. So that will be our formula, C4H10O. Then the final thing we should do is, we've said there's no double bonds here. Okay, we've said there are no double bonds. Is my formula saturated or unsaturated? Is it following that CnH2n plus 2 if it's saturated? It's actually not unsaturated, it's saturated, because this is C4H10, so it's CnH2n plus 2, so C4 times 2 is 8 plus 2 is 10. So this is actually a saturated, and that sort of corresponds to what I've got. There are no double bonds. Remember, if it's saturated, it means there are no double bonds. One unsaturation, one double bond. Two unsaturations, two double bonds. Okay, so it matches a saturation. Okay, let's look at this one. And remember, we start off looking at the molecular ion. We get the molecular ion. I've put it there because you most probably can't read it. It's too small, these numbers, but it's 116 with a little isotopic peak to the right. And it's an even number, so no nitrogens. And it's also not that 2 units apart, 1:1 or 3:1 ratio, so no chlorine or bromine. And please confirm it in this area. No big peaks here, so no halogens. And also no NH over here, and we know there's no CN over there. So your mass spec is supported by your NMR and your IR. They're all telling the same thing. If they start telling contradictions, it means either you've made a mistake or there's an anomaly, but as I say, I've tried something to keep it pretty simple for you. So starting in the normal way, look for the 3000. I've got an alkyl, matches in my NMR. We can isolate that in more detail later on. I don't have a double bond. I do have when I say double bond, a carbon double bond with a hydrogen on it. I do have, though, a carbonyl, and that carbonyl is matched over here. Now you've got to look then, that area, so is it an aldehyde or ketone? No, it isn't actually. An aldehyde or ketone is up here. Okay, sorry, I've clicked over there, and this is the right area for carboxylic acid, but we know it's not a carboxylic acid because a carboxylic acid would show this triangle in the IR. So aldehydes and ketones are over here, and the peak isn't on this side. It's not 200 and above. It's in the area for esters, carboxylic acids, amides, and acyl chlorides. We know it's not a carboxylic acid. From this side, okay, why can we say it's not an amide and why it's not a an acyl chloride? I don't know if this is clear enough to see. This is round about 1720, 1730. Remember, the amides are lower down, 1600, below 1700, sorry, and the acyl chlorides are around about 1800. So this over here says it's either an ester, aldehyde, or ketone. This over here says it's not an aldehyde or ketone. Okay, so the only thing we're left with is an ester. So we know we've got an ester. Now, how many oxygen atoms does an ester have? 2. So we need to do that when we do our formula. So that's just to say we know it's not those because of the position of the carbonyl on the IR. And these over here could be some CO stretches, around about 1000 from for the ester. And these over here could be the CO. Remember, we had the C next to a carbonyl, which is that one, and the C next to an O. C next to an O is normally more downfield. So we've worked out pretty much, confirmed it's an ester, and from all 3 spectra, here where it's an ester, we've simply by confirming that it's not any of the other things, but otherwise we haven't had much from the mass spec yet, but we've certainly used these to confirm it's an ester and to confirm it's not something else. Now to get the formula, if it's 116, we've got 5 carbon environments, 5 peaks. So we know we've got 2 oxygens present, so the mass from the 2 oxygens are 32. So the mass from the carbon and the hydrogen must be the 116. Subtract the 32 from the oxygen, gives me 84. So 5 times 12 is 60. Now, you can't have 5 carbons surrounded by 24 hydrogens. I mean, you can try it. Remember, a carbon can only have 4 bonds, so, and remember, one of them is a double bond, so you need more. And if you have 6 carbon atoms, it works out very well. The mass is 72, so C6H12O2, and it matches 1 unsaturation, CnH2n. Twice the number of hydrogens to carbon matches 1 double bond. Any questions so far? Can we stop? Right, we'll stop here. What I'm going to do is tomorrow I'll just do the recording of the rest of the lesson. I'll just sort of record it because I want this done so people working over the holidays can finish off this spectroscopy standard. Or do you want to be in a lesson? You're busy, right. So I'm just going to record the rest and I'll just have 2 things up for you to look at. Right. Well, have a really good holiday. Well, we're going